We chose to look at food.com's recipe data and create a predictive model to determine the amount of time a given recipe would take to complete. So our research question was, what factors play a role in determining how long it takes to finish making a recipe? We chose to look at this research question because once we were looking through all the data, we felt like there were some recipes that took way longer than expected or were way quicker than expected. So we wanted to see which features actually had an effect or an impact on determining how long it would take for a recipe to finish making. So this is the code for the baseline model where we filtered for anything under 240 minutes, and the only features that we used were the number of steps and the number of ingredients. This baseline model produced an RMSE of 34.8861 minutes with an R squared of 0.0886. We started with this as our baseline because we felt that the most intuitive thing when it came to approximating how long a recipe would take was based off of the number of steps and ingredients needed to prepare the dish. We thought more steps and more ingredients meant a longer time to finish the recipe. And then we also chose to use a simple linear regression model. It came off as a linear relationship where as the number of steps and ingredients increase, there should be a positive linear relationship with the recipe time. So the data that we chose to use was actually the metadata and not the processed data that was provided in the food.com recipe data. We looked at raw recipes and pprecipes.csv files, where in raw recipes we looked at the ID, the name, the number of steps, the minutes, the tags, the step description, and the ingredients, and then pp recipes gave us the ID and the technique. And the data was pulled from food.com's online recipe aggregator, which basically contained over 180,000 recipes and 700,000 reviews, which was collected over the span of 18 years, and was actually used in a paper with Professor Macaulay titled Generating Personalized Recipes from Historical User Preferences. For the data cleaning and processing, we chose to start off with making one data frame first that only contained the variables that we were interested in from both data sets. So in the data cleaning, we had filtered out for any recipe that was listed to take under 240 minutes based off of the IQR. We dropped any NaN values. We converted the tags variable from an array of strings into string literals. And then we also filtered out any tags that were not indicative of the recipe's time. So that included any holiday, such as Christmas or Valentine's Day, miscellaneous tags such as bear, and regional cuisine names such as Italian, Californian. In the data cleaning and processing, here you can see all of the tags that we have filtered out. So this section only includes the region and holiday tags that we went through and filtered out. And then here also the miscellaneous tags and the time tags. We also chose to remove the time tags because they ended up causing us to have a much higher accuracy with the time tags in than the time tags out. This is because the time tags quite literally tell the model how long a recipe is supposed to take. So because of that, we chose to remove those. And then after that was done, all the tag values were multi-hot encoded into the final data frame to be used as features. In terms of data processing, we chose to keep numeric features such as the number of steps, the number of ingredients, but we also engineered additional interaction features such as the prep time complexity and the ingredient step ratio. We also extracted the number of techniques, converted the clean text into a multi-hot encoded matrix. We created text-based features from recipe names, such as any names that had a long cooking time, such as braising or marinating, which we defined as having a slow word. And then we also chose to convert ingredient lists into string literals for pattern matching and binarizing of ingredient categories. Here you can see part of some of our data processing and feature engineering. This is not representative of all pre-processing in our project, but it is part of it.
After data processing, we'll be doing the EDA portion. We will be looking at some summary statistics of the features, as well as our distribution of the variable we're predicting, such as the minutes, the correlation matrices between the features and other features, and we'll be able to also see our variable there, as well as regression scatter plots between our predicted variable, minutes, and the features we've chosen. Here, when we were going into our summary statistics, we actually saw that it was a highly right-skewed distribution for minutes. If we look at the mean, it is around 12,000, where the median is actually 370. So it's a highly right-skewed distribution. In order to get rid of these high outliers, we decided to use IQR. Through IQR, we were able to get the mean down to 44.83 and the median to 35. So it's a way better change than what we had before. And we used 248 as our upper bound. This is what we can see visually, so you can see it better. This was before we did the IQR filtering. You can barely see the distribution, and you can see that it's very far. However, here after we filter, you can actually see the distribution, and it is still right skewed, but it is more manageable for our model. Here we have regular correlation and the absolute correlation. It's very important to use absolute correlation so you can actually rank from most correlated to least correlated without worrying about the negative sign in order to get the actually highly correlated values, not depending on direction. And so here you can actually see that there is a difference when you do this. Like instead of yeast being the most highly correlated, it was actually 4, 1, or 2, which was probably negative since it wasn't here in the regular one. So we use that in order to get the features. However, we still understand the correlation is negative. With this, you can actually see the correlation matrix between the variables and the other variables to variables on the top 100. However, it's very hard to see. Majority around the 0 portion with it being blue. So let's try to zoom in and maybe the top 25. Here we can actually see more yellow and more purple. So we have negative and positive correlations that are stronger. And then let's look at the top 10. Here we can see correlated negatively right here. And so here you can see much better how correlated these features are to each other, especially with minutes. And this is our top 8 features that were the most correlated with minutes. If you can see, majority of them are binary features, like 0, 1, like weeknight or not, for 1 or 2 or not. A small amount are actually like consecutive ones, like number of steps and ingredients. So we can actually understand better what we're dealing with.
So next up is the modeling section, and some of the modeling context is that since our predictive task is formulated as a regression problem itself, so the goal is to predict the total recipe cooking time. Some of our inputs include numeric structure features, text-derived numeric summaries, multi-hot encoded tag features, cooking techniques, binary ingredient category signals. These are some that we will be using as features in our models. And the output is the total cooking time in minutes. And our goal is to minimize error between the predicted time and the true cooking time. We will be evaluating our models based off of R-squared, which is the explained variance, and RMSE. Some of the appropriate models that we planned to work on is the linear regression model, which is the same as the baseline, and with OLS and Ridge added. And we will be comparing them to tree-based models. So before working on the actual models themselves, some of the advantages and disadvantages that we expect to have for linear models is that they are extremely efficient to train, even without a large number of features. And it produces coefficients that allow us to validate logical relationships as well as minimal risk of overfitting. However, it cannot capture non-linear relationships well, and all the features are weighted globally, even if only one recipe uses like a certain ingredient or technique. As for tree-based models, they can help capture non-linear relationships, but may produce inaccurate results for linear relationships and also has a high computational cost. We also chose to test our model on different levels of filtering. So although our baseline uses less than 240 minutes from the IQR, we decided to also test out some smaller increments of the recipes that take a smaller time frame. So starting off with the first model that we built after our baseline model, this is very much built off the baseline model, and we just added in more features aside from n steps and n ingredients, and we also applied shrunken mean text. So the first setup is very similar to the baseline model, and then we added in tags, which has been filtered out during the data cleaning part. It's because we wanted to select those tags that we think are most relevant to the length of the recipe, but we excluded tags that are very specific in providing the time. Then we also added in techniques, which comes one hot encoded as a string and requires some parsing. And then we created some extra numeric features based off of the steps and ingredients text columns that come in the CSV file. Specifically, we looked for word counts, character counts, and the number of unique words, because the more complex and long the list of steps and ingredients may be, the longer it might take the recipe. And then we decided to add shrunken means on end steps and end ingredients from the baseline model to help reduce sensitivity to outliers of recipes. And then we compile all of it here. So for this model, we see that the result of r squared comes out as 0.3643, and which is like much better in comparison to the baseline r squared that we ended up getting. But we believe that the result can be further improved, and which is why we worked on the next model. So for this model, we added even more feature engineering, and we also had a focus on ingredient features. So starting off with the same setup, we added in more numeric features. The first one would be the ingredient step ratio. This tracks the density of ingredients for each step, which we thought would be an indicator for the time taken for each step and hence the recipe as a whole. And we also added in prep complexity. This helps scale the number of steps more over the number of ingredients, because when we think of it intuitively, the number of steps might indicate more work put into the recipe and hence the time. And we also combined steps and ingredients as an interaction terms feature. Then another thing that we added would be the text feature here. We looked specifically for words that may indicate slow in the steps or a long time in the recipes. So you see words like slow, braise, stew. These are all steps that would take an extra long time in comparison to others. And then we did a lot of engineering on ingredient-based features. We extracted the different types of ingredients that may be in a recipe. So here we has meat, rice, potatoes, squash, bread, dairy, tortilla or crust, and processed, because the different types of ingredients also indicate the time that's gonna take into preparing these. For example, meat, potato, squash may take longer time than tortilla or crust. And we also combine some of them with the slow words that we extracted, because meat, if we're doing a meat stew, it might take an extra long time, but if the slow words are with a processed food, then it might not take as long. We also filtered out some of the indicators for short times or fast cooking. So like has quick, instant, oven. These are all words that might indicate a short cooking time. And then lastly, we combine all of these features. So for this model, we can see there's a significant improvement in the results of having a 0.4563 in comparison to the linear regression model we had previously with not as many features, and also the baseline as well.
Now we'll be looking at the tree-based models. We will look at actually the data preparation we did for both models that we found. We got our techniques, that is a hot encoded variable, and we exploded it, so we have a bunch of features for it instead of it being one feature. After that, I just selected the top features that are most correlated with the absolute value, and then I just got the top 100 features. So it's a very simple preparation, and you might be thinking why I wouldn't be using feature engineering. And the thing is that I did use feature engineering, and I got worse R squares for it. So I kept it simple and more accurate with no feature engineering. As you can see, I also have these portions of my cutoffs of 60, 120, 180, and 240. Those are the cutoffs we talked about beforehand of the different minutes in order to see how our models react. This top portion is what I just explained to you guys of setting up the data set. And here we're actually making our training data set. We're scaling it. And then I tried 4 different models: random forest, gradient boosting, histogram gradient boosting, and then K and then N. And what we can see, our best ones turned out to be random forest and histogram gradient boosting. So now with random forest, so here we have just our train and test set We fitted it to a random forest regressor with its default settings of 300, none, 1, -1, and 40. We train it, we get our scores. And so with that, we changed each one so it could be under 240, under 180, under 120, and under 60 minutes. And with each one, we can see how our R-squared and our RMSE improve and don't improve. And so as we decrease, we begin to improve our accuracy. However, it gets to a point where we take so many points off that it honestly makes it worse. So we decided to fall back on 120 minutes as our upper bound, and it got us to 46% of our variance explained by our data. And so that's a very good improvement compared to what we had with the linear regression. And so then now, random forest, the model has optimal parameters or hyperparameters that can be chosen. So what I chose to do is that I wanted to have the most optimal random forest. So I decided to test a bunch of different hyperparameters in order to see how it reacts. And with this, we actually get our optimal parameters. So then now we will just be fitting it regularly in a test train validation set and our CV in order to see if it's actually overfitting or not. And we get a mean of 0.48, which is very similar to just the regular one that we did, which was 0.4849. So this shows that it's not overfitting and that this is a good general model. So then with this, let's look at overall what we have. Our MSE turned out to be 16.9 with our R-squared being 0.48, which means around 48% of our data of our variance is explained by these features. As I said before, I chose the top 100 features, and these turned out to be such as the first index of the feature from the hot encoded list, the number of steps, number of ingredients. And so I just chose the top 10 most correlated with minutes. The reason I chose to do random forest was due to its ability to handle nonlinear relationships between variables, which is something the linear regression couldn't do and might be why our R-squared is higher than our linear regression. So I could reduce some noise from not using all the features, but focusing on the strongest predictors. And then I tested all the hyperparameters to tune it and get the best random forest possible. So now we've gotten to our final model, but you might be wondering, wait, we never talked about histogram gradient boosting. And that's because that is our final and most optimal model. Like before, we did the data processing that we talked about beforehand for random forest, which is the same one as this histogram gradient boosting. This is very similar, almost the same as random forest. And the small differences are just stating that we'll be using a histogram gradient boosting. And with this, similar to random forest, filtering of 120 minutes was the best one. However, it started decreasing after we decreased the minutes filtering. So we kept it at 120, similar to random forest. I wanted to have a more optimal model, so I decided to test it on a bunch of hyperparameters of the histogram gradient boosting. And with this, we were able to see that these are the hyperparameters that were chosen, that were the best one. So this is the most optimal one. So let's actually see what our R-squared is based on these optimal parameters. And so with our train and test, we see that it did actually increase it. It was at 0.49 and we got it up to 0.5 fully, so a full 50%. And this is really good compared to what we had with linear regression. And it is a slight improvement from random forest. We will also check if it's overfitting or not with our CV, and we can see that it's around the same, similar to random forest, just that it's a little higher. So we can state that it's not overfitting. And so this is what it turned out to be. Our RMSE is 16.70, and then our R-squared turned out to be 0.5. We use the same metrics, 100 features. So you might be thinking, why would we choose this one over random forest if they're around the same thing? And the thing that's actually different about histogram gradient boosting is that this one is actually very fast. And it's due to its ability to model nonlinear relationships very effectively on tabular data. Let's look at our final model results, which is the same as before. With histogram gradient boosting, the main reason why it's chosen as the best one is due to its processing time. The linear regression and the random forest models were very much slower compared to histogram gradient boosting. Like we saw before, histogram gradient boosting took 3 seconds to fit this entire data set, whereas random forest took around a minute to actually train this whole thing. The R squared of histogram gradient boosting and the R squared of random forest is very similar. However, its ability to be more efficient makes it be so much better than linear regression and random forest that it must be the optimal model that we'll be using, as well as it being slightly higher than random forest as well.
In terms of related work, we found 2 separate uses where similar work that used the same data set had been accessed. So the first is from Professor Macaulay's own work in generating personalized recipes from historical user preferences. Their goal was to work on essentially generating and creating a personalized recipe for users who had a preference in certain recipes and cuisines, but simply didn't know the ingredient names or the terms used in those types of recipes. And then the second piece of work that we found that used the same data set was predicting cooking time based off of different recipe features. And in this one, they had a similar research question where they attempted to create a model that would predict how long a recipe would take given its ingredients, steps, and nutritional content. In their case, their baseline model produced an RMSE of 87.3 minutes, which in comparison to their baseline, we have a better RMSE at 34.8205 minutes, which is more in line with their final model's performance instead. And this may be due to the fact that they chose to look at nutritional content over other data. And then looking at their final model produced an RMSE of 34.35 minutes. And in comparison, our final model produced an RMSE of 16.7034 minutes, which is about half compared to theirs. And in this case, our final model was using hist gradient boosting regression, as where theirs was only using a linear model with additional features. We used a different model and provided additional features and conducted some feature engineering as well, which was probably the reason why our model for baseline and final model improved better than theirs.